Hello, I hope everyone is well. What I'd like to do, two short videos, I hope they're short, right, is do a review for the exam 2 coming up, covering chapters 6, 7, 8, and 9, Introduction to Inferential Statistics in number 6, Confidence Interval Parameter Estimation of 7, the 1 sample case of 8, and the 2 sample case of chapter 9. So I'll do this one. That covers chapter 6 and chapter 7, and then I'll close this one out and then change the stuff on the whiteboard and come back to you with chapters 8 and 9. Even though I'm doing these separately, we want to think of them as a logical sequence. It is inferential statistics, where we are moving from drawing down a sample from a population, taking that point estimate and closing it in a confidence interval, looking at trying to estimate a parameter. In those circumstances for chapters 8 and 9 where we know the parameter, here we're trying to discover the parameter, estimate it. In chapters 8 and 9 in the next little video I do, we do know the parameter, and what we're trying to do is find that the value of our sample that we've drawn is statistically significantly different than the population parameter, and I'll talk more specifically about that. But there is a logical progression from 6 to 7 to 8 and 9. Inferential statistics remains in the background. 7, the parameter is unknown, and chapter 8 and 9, the parameter is known. Okay, so let's talk about this. One thing that you want to do as a way of reviewing these 4 chapters in preparation for the exam, I can tell you that it is 120. It's 60 multiple choice questions, like the previous one. They're conceptual questions. You've already demonstrated your capacity to do the calculations with the homework, and we had some concept questions on there. So these are mostly conceptual questions. So there are 60 at 2 points each, and A is between 90 and 120. So that if you score something over 100, that's a little extra you have at the end of the semester when I sum up all the exams and divide by the number of exams. So maybe you'll come out with a little higher average if you can get up to 100, 101, or 120. And I'll be putting that up on Blackboard in a couple days. This is Tuesday. On Thursday, so it'll be available to you sometime on Friday, but I'll let you know by email. Okay, chapter 6, the Introduction to Inferential Statistics. Here you can see, as we've talked many times, the idea is to, the parameter is unknown, to know what that parameter is. But the pathway from the population to parameter is prohibitively expensive, both in time, personnel, costs, and all that sort of thing. So we draw down a sample, and from the sample we get a statistic. Then that becomes an estimate of what that parameter is. Now there's some important considerations and concepts, shall we say, practices in deriving a good sample. One is that it's random. There are a number of different kinds of illustrations of types of samples in chapter 6. You don't need to be concerned with that right now. Know that it's random, and that we're talking about the EPS-EM, equal probability sample method, so that everybody, whatever method that you use to sample, that method creates the opportunity of equal opportunity for everybody to participate, however you draw that sample down. That will make it representative and will also make it unbiased. This is a bolded term from chapter 7, and pay attention to the bolded terms in these 4 chapters, because very likely around those are constructed some concept questions in the exam. So if we have a random, representative, unbiased sample, so that the dialogue with the sample is very similar to the dialogue we would have had with the population, so that the sample is representative. If this is like 60% Mexican origin, then this would be about 60% Mexican origin. If this is 40% male, then this would be about 40% male. So the internal dynamic is similar. So any dialogue we're having with the sample is essentially the same dialogue we'd have with the population. When we get to the statistic, this is our estimate of the parameter. It's the inference that had we gone this way, inferential, had we gone this way, we would have found as the parameter basically what we found in the statistic. Now, the central limit theorem is a very important theorem in chapter 6. It basically says that as the sample size gets larger, as the n gets larger, the estimate becomes more efficient. Things, if you'll recall, as the normal curve becomes more heaped. It becomes more heaped. At something less than 100, it would be a flatter curve, if you recall. You can see those illustrations in the text. A more heaped curve is usually one that we think of as something larger than 1 or 100. The larger the sample size, the closer you get to 500 or 1,000, the more heaped this curve becomes. And you'll see illustrations of that. So the central limit theorem is an important piece of this, because you want to focus on your sample size, really, to become more efficient in your estimate of the parameter. Now, what we get from the statistic is a point estimate. This, say we're using a mean, we're trying to estimate the age up here, and we get an average age in our statistic. That's a point estimate. So I want to keep that concept in mind. The other part, as we move into Chapter 7 here in a minute, particularly in Chapter 6 still, that says parameters, what that's supposed to say, unknown. Here we've got three, you'll notice in Chapter 6, three distributions. Your population distribution, your sampling distribution, and the distribution of your empirical sample. This one you can see. It's the empirical sample of your data. These two are hypothetical. This is the one that we assume to be normal if we're talking about a million people in San Antonio, let's say, and we're looking for the average age. We can probably, on a continuous variable like that, assume that it's some kind of normality. This mu that we have here is a Greek denotation for mean in this case, and these are the standard deviations that we would have down here. Remember, these are standard deviations, 68%, 95%, 99%. The limitations of the distribution, x's in our frequency distribution, and the mean of that x. What we're saying here with the point estimate, if we were to, we know as statisticians, if we were to draw down 100 samples of the same size, let's say we're doing 1,000, 100 samples of the same size, 1,000, n of 1,000. If we drew down 100 samples of the same size, each one of those would have a different composition of individuals in it. 1,000, the mean of one sample would be slightly different than the mean of another sample. So this is a point estimate. We have confidence in it because we've taken care to be random, representative, and biased. Epsom, good central limit theorem to get good efficiency and our estimate. We're comfortable with this, but we know there could be some variation if we did 100 samples. The sampling distribution then is that intervening distribution in between the two, and its value is that it is the distribution of 100 hypothetical samples. Again, if it's 100 or greater, central limit theorem, it takes a normal distribution. So this normalizes, that's why we sort of draw it this way. And whereas these are standard deviations, demarcating limits within the distribution, these are called standard errors. They're exactly the same thing as here, but when somebody says standard error, you know you're talking about the sampling distribution. Somebody says standard deviation, you know you're talking about the empirical sample. So what you want to imagine these are the distribution of 100 samples, so that on the left-hand tail you've got the small sample, on the right-hand tail you've got the large sample, and then you've got all the other samples in the heap in between. That is the histogram that is in the back of these normal curves. The other theorem in Chapter 6 says that the mean of the means, the grand means, the mero-queso mean, of the means of the sampling distribution is the mean that's up here in the population. That's the other theorem to keep in mind. Okay, so these are very important principles as we think about the inferential statistic piece of Chapter 6, and this is the methodology of getting us the good estimate of what this parameter is, which takes us to Chapter 7 over here. Now, Chapter 7 is the estimation of the parameter unknown. It is a confidence interval. We know this is a point estimate, so if we were to draw down 100 samples of the same size, that would give us some additional confidence that we have a good point estimate, even though we're pretty good confident about this because of the process we've taken. So the confidence interval tells us that here you can see I've demarcated here the second standard deviation or standard error either side. That encloses, if you remember from Chapter 5 and 6 and 7, encloses 95% or 95 out of 100 of the possible parameters inside those two standard deviations plus or minus the mean. So when we get over here, the confidence interval in statistics, generally in social statistics, we speak of 95% or 95 out of 100 with an error rate of 5 out of 100. Now there are some other ways we can do this we'll talk about in a second. So the standard confidence interval would be 95 out of 100. So here again, you've got the low mean and the high mean and the main mean, which from that other theorem we say is a good, probably is the precise measure of what this value is up in the population. Now the assumption in statistics is within this confidence interval 95 out of 100, the true parameter is likely to exist. We're pretty sure it exists, but we know there's some variation. But we say 95 out of 100, it's likely to be inside plus or minus 2 standard errors around the mean. So anything that is within these 2 standard errors around the mean are similar. Anything that would be outside that, any values or means outside that interval, we would call dissimilar. That's very important as we move into chapter 8 and 9 here in a few minutes. So the confidence interval 95 out of 100. Now the question comes, why would we not want to use 99 or 90? Well, as confidence intervals. There are some good illustrations in chapter 7 about that towards the end of the chapter, but basically, if you did a 90, let's say, if we did 90, let's say we drew it about right, that's not working so well, is it? And we drew it about right here, then we've got some pretty good precision, but we have a whole lot of error outside that. That's 10 out of 100 chances of being wrong. 95 is 5 out of 100. We might get precision, but there's an increased amount of uncertainty over here. All right. If we were to, let's see if I can get this out of here. If we were to do the 99 out of 100, let's say the 99 confidence interval out here, where we're enclosing all of this, where we have an error of 1 out of 100, we'd say, well, that's pretty precise. The problem with that is while we got low error, 99 out of 100 of these are inside the standard error of 99 out of 100. You know, it's not very efficient, is it? It could be anybody inside that. Only one is not in there, so 99 are in it. How do we know which of those 99 is the true parameter? So we lose kind of an efficiency. We lower our error, but we lose efficiency. With 90, you get pretty good efficiency, but you got a whole lot of error. 95 splits the difference. 95 gives us pretty good efficiency and very little error. So I think that's basically why statisticians of social sciences rely on the 95 out of 100. So rather than moving the confidence intervals, which you may have to do from time to time, the real way to drive this is with your central limit theorem. The larger your sample size, the lower the standard errors and the lower the standard deviations. You saw this back in chapter 4. The larger the n, the smaller the standard deviation. If this is say a sample size of 100 and you've got a shape like that, or you've got a sample size and it's like this, well, it's supposed to be standard errors, let's say, or you've got one that looks like this, you can see that the space between these is very narrow, much narrower than here. Think of the geography of the distribution. The larger the sample size, the narrower the geography of the standard errors and the standard deviations and standard errors become. So really, in order to get more precision, it's not really about moving confidence intervals. It's really driven by the central limit theorem. Always opt for as large a sample as you can afford, because that's where you get your efficiency. Okay, I'm going to come back in a few minutes.